So let's give a, so we will give an introduction and then discuss our algorithm and techniques. Okay, so let's start. Let's start with the Fourier transform. So we know like a Fourier transform is a conversion between the time domain and the frequency domain. So in this talk, I always draw my singular on the left-hand side. So this T means the time domain. So Y is a singular, and this is his Fourier transform. I use Y hat to denote the Fourier transform of Y, and F means the frequency domain. Okay. So this is the original signal. This is his Fourier transform. So one basic fact about the Fourier transform is the algorithm fast Fourier transform for n points just of time like n log n is ubiquitous in algorithm design and numeric computation. So it has lots of applications in engineering and science. Okay. So how many of you know this algorithm like F? So in this talk, sometimes I will just call this FFT. It's like one of the most important algorithms in computer science. It can so basically given a data point of given data points of size n, so it computes the n Fourier coefficients in time just n log n. Okay. So one particular reason that the Fourier transform is so useful is that many real-world signals are approximately sparse after the Fourier transform. For example, like this fact is a key point in audio compression and image compression. So let's take this signal as a concrete example. So basically, what I mean is that so there are like 5 dominating frequencies in the Fourier transform. So if I just take these 5 Fourier coefficients out and erase or like negate the rest Fourier coefficients, so this gives a pretty good approximation on the time domain. So I take this, I take these 7 frequencies out, and then I use the Fourier coefficients and I erase the rest. So then on the time domain, so it gives me this like blue line, which is a pretty good approximation. Okay. So this raises a very natural question. Suppose this like a sparse approximation, like in blue color, is the truth that we are interested in. But given the noisy data in the red color called Y, so how can we find the true sparse representation? Okay. So in another word, so my input is a signal Y whose Fourier domain is dominated by a few frequencies. Say the sparsity parameter is K. For convenience, we may assume K is a constant in this talk, and the goal will be to find these K frequencies and then learn the truth X. Okay. So one remark here is that for this talk, we will assume K is a constant, but you can choose any parameter K that you prefer. And another thing is like while this sparse parameter K has been given, we do not know the location of these dominating frequencies. Otherwise, the problem is just a linear regression to find the Fourier coefficients. Okay. Yeah. So this is the Y. Okay, how can I hide these? Oh. No. No. Okay. Oops. Okay. Okay. So this is the problem that we are going to discuss in this talk. So given excess of the noisy data Y, we want to find out these like dominating frequencies and learn the sparse representation X. Okay. So you may realize that one lazy way to do this is just to run the faster Fourier transform whose running time is n log n. Then I look at these I look at all Fourier coefficients and take out the K largest. But this has running time like n log n, as I mentioned before. But our goal will be more ambitious because we are just interested in like these K dominating frequencies. So we want an algorithm whose running time is polynomial in k and log n instead of like n log n. So we want to think like k is a constant. So basically the running time should be polynomial in log n instead of like linear in n. So that's our goal. Now sometimes we call this problem like sparse Fourier transform. You can think of this as like I want to leverage in the prior knowledge of sparsity k into a fast Fourier transform algorithm. Okay, so let me know if you have any question or feel free to stop me. Okay, so this is the basic problem. So let's review some previous results about the discrete setting. So in the discrete setting, we have successfully obtained like a running time k log n or tilde k log n. So tilde hides some like small minor factor, but basically we get the correct running time k log n. K is the sparsity, and the log n is because we have noisy query on the signal. So every time you can consider like like every frequency has n possibilities. So we need the log n binary. We need the log n binary search to find out the true position. Okay, so k log n is the correct answer. So in the discrete setting, we do have such algorithms. For example, in the Boolean cube and in the cyclic group of size n. So actually, those algorithms are not studied from the original. So actually, like the first research is not from the perspective of Fourier transform. So Goldreich and Nevin studied this to construct like pseudo-random generators in cryptography. And then another classic work by Alcavia, Goldwasser, Safra, they studied this as list decoding of Hadamard codes. Okay. I do not have time to go over this, but so I just want to say, like this problem has rich connections to many areas in computer science. And in cyclic group like Hassan, Indig, Katabi, Price, they obtain like very efficient algorithm for the cyclic group, which has lots of applications in signal processing and then like GPS or like a wireless transformation. Okay. So in this talk, we will focus on the continuous setting. So the Fourier transform will be defined over the real line. So this means that like for a singular xt, the Fourier coefficient of frequency f is x hat f is the integration from minus infinity to positive infinity. This single xt times the wave function e to the 2 pi I times ft. Okay. Okay, so this was just some terminology. So the k Fourier sparse signal, this is the truth that we want to recover. So we will use xt to denote it. So this will be the summation of k basic wave functions. So each basic wave function has an amplitude Vj times e to the 2 pi I fjt for arbitrary frequency fj here. Okay. In fact, like to define the problem formally, I should go over the Dirac delta function, but just for ease of exposition, I will skip that part. Okay. So through this talk, the signal that I'm interested in is this is this xt in this form, like summation of k wave function. Okay. So while the definition is over the real line, like a computer cannot handle like arbitrary large real numbers that goes to positive infinity or negative infinity. So we will assume like there is a time window on my signal. This is saying like I cannot observe like a time that's like infinite away. So I'm going to only observe my signal in this time window, which is drawn as the blue line here. Okay, this blue line means my time window. And I also have noise access on the true signal. So basically, this means like I can query. This means like my input data or like my access is on y, which is the summation of this true sparse approximation, true sparse representation x plus some noisy. Okay, and I can query my input signal y on any point in this input data, on any point of this time window from minus t to t. Okay, and the goal is still to recover the dominating frequencies, and then we can use the inverse Fourier transform to get a good approximation on the time domain. Okay, so this is a problem. Let me know if you have any question. Okay. 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 So next, let's discuss like a very natural attempt. So since I have told you that we have like a success, we have a we have a successful line of research on discrete domain. You may ask, why not we just reduce the continuous problem to the discrete problem? The reason is like the continuous sparse signals are fundamentally different from its discrete counterparts because these frequencies f1 to fk could be arbitrary real numbers. So sometimes this is called like off the grid. So let me explain what do I mean off the grid. So probably you know like periodic signals. So remember, so in here, so in this four pictures, so the time window is from -1 to 1. So the easiest case is like the signal is actually periodic from -1 to 1, like here. So you can see like so this signal repeated like 3 times. Okay. So in here, like you know, like actually I know everything of my signal from this limited time domain, and you also know like all the frequencies will be on the grid of like half. This is periodic signals. So in this page, I will use eta to denote the frequency gap, which is defined to be the minimum gap of 2 frequencies in my signal x. Okay, and we know like for periodic signals, so eta is 1/2t. So sometimes I call like when the signal is on the grid, this means like all frequencies are like integer multiples of 1/2t, but the t is like 1 here. Okay, but things get changed like when we allow arbitrary real numbers. For example, like so this is a signal whose whose frequencies are larger than this grid 1/2t. So then it is no longer periodic, but you can still see like in this limited time window, this signal contains lots of information. But things becomes weird when the frequency gap, or like say like when my frequencies get like closer and closer to each other. So this is an example. So the frequency gap is below half, or means like for example there are 3 frequencies in this interval of -1. So you can see like the signal in my time window. So its energy is relatively small compared to the signal outside of the time window, and things become worse if the gap of these frequencies are smaller and smaller. So my signal, I only have my observation in this time window, but it's relatively small compared to the outside. Okay, so things get changed like when so when these frequencies are arbitrary real numbers, so this is like one fundamental bottleneck compared to the discrete setting. Okay, so that's weird. How can I show the last 9? Okay, I don't know. Okay, let's forget. So let's review some previous results. So of course, we are not the first to study this problem. So actually, this problem has a very long line of history. That's even before like we invented computer science. It's like so the French mathematician Prony first studied this problem in 1785. So he invented a method based on polynomial interpolation. So the great news is that like it only takes 2k minus 1 queries on the input signal. But unfortunately, this method is very sensitive to noise, so it has an extra requirement that the noise added to X should be very, very small. Okay. So then I will discuss another 2 lines of research. I will use one more notation. So recall like eta is still the frequency gap. But while we allow these frequencies to be arbitrary real numbers, we still want to put a limit because the computers cannot process like a arbitrary cannot handle like a frequencies goes to infinity. So I assume there's like a band on the frequency limit that's -f to f. Okay. But then we can discuss the second line of research. So this line of research is initiated from the Shannon-Nyquist sampling. So it takes basically OFT queries on the input signal, and its running time is polynomial in FT. But it still has another requirement that the frequency gap has to be at least 1/2t, similar to the periodic signals. So this is 1/2t we have discussed before, is the gap of periodic signals. So recently, not recently, like 10 years ago, motivated by the discrete sparse Fourier transform algorithm, so there is another line to study, to use the technique still. So they can reduce the query complexity to to the correct order, or this is the correct order in our opinion. That's basically k times log ft. So k is the sparsity parameter, and ft is basically the size of the problem. Okay, and then but it requires the frequency gap to be even larger, something like log k over 2t. Okay, so these are previous results on this line. So we can see that so the first line. So one thing I didn't say is I only discussed the query complexity here because all algorithms have time complexity that's polynomial in the query complexity. Another reason is for many practical applications, it's more expensive to take a query on the signal instead of a computation is cheap nowadays. Okay, so this. But if we take a step back, we can see that all these methods have some drawbacks. So the first method requires the noise to be very, very tiny. The rest of the two requires a frequency gap. And in fact, the frequency gap is also necessary if we want to recover these frequencies. So here is a very simple example. So I have two signals in green color and black color. So while they are quite different, because one of the frequency, so one of the frequency gap is 0.3, another one has a frequency gap that's basically 0.2, but they look quite close to each other in this time window. So this is saying if the noise is adversarial, then he can erase the difference between these two signals such that you are unable to distinguish them. So this is also saying, because we cannot distinguish them, there's no way we can find out these frequencies. Okay, so this is saying actually this example is given by Anka saying this requirement on the frequency gap is necessary to recover all the frequencies. Okay, so recall our goal was to find these k frequencies and learn the true sparse approximation, the true sparse representation xt. So the main question we want to answer is what can we learn without the condition without the condition that eta greater than 1/2t. Okay. Okay. So our intuition is while we are unable to recover those frequencies exactly, we can still learn the signal, as a whole signal. Yeah. So that's basically our point. So we will not recover those frequencies accurately, but we will learn the frequency as a whole. Yeah. So this is our main theorem. So this is saying for any k Fourier sparse signal xt and any noise function, so it could be adversarial. So our algorithm takes basically k to the 4 times log fd queries on the noisy input y, that's the summation of the sparse representation and the noise, to find the approximation x tilde of x. But this x tilde is just the approximation of x on the time window from -t to t, because the query access of y is also in the same time window. So we will only guarantee the approximation in the time window. So what I want so some remarks. So this, to the best of my knowledge, so this is the first robust algorithm without a frequency gap assumption. And if we want to measure the distance between x tilde and x, in this talk we will use this expected L2 norm distance. So this means that since we only care about the time window, so I will define it for the time window. So I use this notation T. So this means I look at a random point in the time window, the expected square of GT. Right. So this is the definition of the expected L2 norm, and our guarantee will be that the distance between x tilde and x in this expected L2 norm is at most 1.01 times the noise plus like a tiny constant times the L2 norm of x itself. Okay, so this constant we can make it to be arbitrarily small, but this one, since the noise can be adversarial, so 1 is necessary, and we can get this arbitrary close to 1. So that's the guarantee of this approximation. And our running time will be quadratic in the number of samples. Okay, so you can think of this is like faster than the naive algorithm of running time, basically f times t, when k is a small constant. So any questions so far? Yeah. Okay. Yeah. So this is our main theorem. So next I will give some application. So the first application is to go beyond sparsity. So you may say, so the algorithm is tailored to sparse Fourier transform. So what can we do if the Fourier spectrum is not sparse but looks like some like multi-bands or some like Gaussian? Okay. So the beautiful work by so then like subsequent work by Aaron, a couple of Moscow brothers, and then and others, they have shown that we can reduce like a simple Fourier spectrum like this to a sparse case. Okay, so here is an example. So the red signal whose Fourier spectrum is supported in this band. So this is his Fourier spectrum of the red signal. So we can find a pretty good like 5 sparse approximation. So this will be my frequencies on the Fourier domain. So there are only 5 non-zero frequencies, and then it gives a pretty good approximation on the time domain. So but of course like we need to to show this for general signals, that's not an easy job. But anyway, like that beautiful work give us the reduction such that we can apply our algorithm to learn like any signals whose Fourier spectra admit a sparse representation. Okay, so this is one application. So the second application is to approximate like Toy-Bliss matrices. So Toy-Bliss matrices is a special type of matrices like whose entry are the same on every diagonal. Okay. So the definition is saying like for D times D Toy-Bliss matrices, it is just defined by 2D minus 1 elements, like Aij is equal to a sequence Ai minus j. So this Ai minus j will go from minus D minus 1 to plus D minus 1. Okay. So Toy-Bliss matrices has lots of applications in computer science, engineering, and physics. So one particular reason is that we only need to store like a 2D minus 1 elements. Another reason is that it admits a Fourier decomposition such that we can use faster Fourier transform to accelerate its computation. So the Fourier transform is saying like you can, so there is a diagonal matrix kind of like his eigenvalues, and then like we will times like a Fourier matrix and his transpose to the diagonal matrix, we will get the exact Toy-Bliss matrices. I don't have time to go over the detail, but the basic point is saying like because of like this is like the so this is a diagonal matrix, so you can think of the elements on the diagonal as the amplitudes, and then these are just like standard Fourier matrices. So the rough point is saying like when the Toy-Bliss matrices admit or like has like a low rank approximation, then we can we may be able to apply the K-Fourier sparse algorithm to approximate those matrices. I think that's at least my understanding. Maybe Jerry has a better sense. Yeah. So this is the second application. So that's all I want to say in the introduction part. The rest of the talk. So the main thing I want to answer is like how we characterize signals. Oh, sorry, this should be next, or this should be at the most. So how to characterize signals whose frequency gap could be arbitrarily small. So you have seen that so when the frequency gap is not 1/2D, signals may behave like arbitrarily. Okay, and then if I have time, I will discuss some tools in the algorithm design, like filter functions and importance sampling. So this is a rough run. Let me know if you have any question. Okay. So the next part is our algorithm and technique. So let me say, let me give another reason that the frequency gap 1/2T is the bottleneck of previous algorithm. So David Hilbert, this is a famous mathematician. So he proved this inequality, saying while so my frequencies doesn't need to be on the grid. As long as I can guarantee the gap is greater than 1/2T, those signals will behave similar to periodic signals. So recall this is a periodic signal. So this is a period. And this is a signal, so this is not a periodic signal on the time window. But this inequality is saying okay, but it's still fine that this time window will have enough energy to recover the frequencies. Okay, this is so to say this exactly. So David Hilbert proved that the expected energy in this time window is roughly the summation of the Fourier coefficients of x hat. Okay. Unfortunately, this is false when eta is less than 1/2T. And that's essentially why our previous approach requires this gap greater than 1/2T. Okay. So we want to understand. So back to our problem. So we want to understand the signals whose frequencies are not separated. So we will call them clustered. Clustered means the frequencies can be very close to each other. Okay. So for easy of exposition, we will just consider signals whose frequencies are very close to 1. Say clustered in an interval, say from minus delta to delta. You may think of delta as a pretty small constant, 0.1. Okay. So of course, in this example, delta is something 1.5, but you may think of delta to be a pretty small constant. So this means all the frequencies of my signal is around 0. Okay. So we want to understand what does these signals look like. Okay, when the frequencies are clustered around 0. So our key lemma shows that when the frequencies are around 0, we can use a polynomial to interpolate the signal on the time domain. Okay. So this is the key lemma, which says for any x whose frequencies are in this interval from minus delta to delta, then there will exist a polynomial of degree that's delta times the time window t plus k cubic. So k is the number of frequency such that this polynomial will close to the signal in the time window. Of course, you kind of believe this from these two examples. When the frequencies are kind of close to each other, this looks like a smooth polynomial, and similar things. It is not that kind of smooth on this side, but you can still, use a higher degree, as we said, the degree goes from the sparsity goes from k equals 3 to k cubic in the degree. So it's believable that we can use a polynomial to interpolate this part. So I will try to give a sketch how we obtain this lemma. So to do this formally, we will apply a net argument on the frequencies and then do Taylor expansion. But due to the time limit, I will just discuss the Taylor expansion and the key component that suppose us that suppose this Taylor expansion. Okay. So the intuition is like if I just look at one basic wave function or like one sparse signal e to the 2 pi ft, so it will have a pretty good Taylor expansion of degree basically delta times t. Why? Because I only care about the signal in this time. I only care about the signal in this time window. This means like t is at most capital T. So then so then I also know like if f is between, sorry, this is minus delta to delta, f is bounded by delta. So after the Taylor expansion of degree delta times t, so the rest part will be negligible. Okay, of course, like the real problem is to prove the Taylor expansion of the k Fourier sparse signal is good. So we want to understand, so you know, like if we do the Taylor expansion on each wave function, so the real question becomes to understand, you know, like the error of the Taylor expansion will depend on these coefficients v1 till vk, and we know like the approximation guarantee we want to obtain is the expected L2 norm of x. We have seen this before. So the real thing or like the issue is like we want to understand the relation between the expected L2 norm and the Fourier coefficients. Okay, so you know, like back to previous slides before. So Hilbert's inequality give us this relation when the frequency gap is greater than 1/2t, but we want to go beyond this. We want to go below like 1/2t. So that's essentially what we want to do. Okay, so I will give you a sketch. So we will use linear algebraic tools to understand this part. So the basic thing is like we want to think of xt is a linear combination of k wave functions. Okay, so then I would like to think of each wave function as a unit vector. So equipped with this expected inner product. Okay, so this corresponds to this matches our definition of the expected L2 norm. Okay, so xt is just a linear combination of these k unit vectors. So as I said, like we want to understand the relation between the L2 norm and the Fourier coefficients. So this is the same as saying we want to understand the contribution of the first vector versus this linear combination. So if we think of it as linear algebra, we know like this vector will contribute at least his Fourier coefficients times the orthogonal part. The orthogonal part means like this vector that's orthogonal to all the rest of vectors. So there is like a parallel part which may be cancelled with the rest of vectors, but we know the orthogonal part will left, no matter what happens. And now to understand this orthogonal part, we know essentially this is the distance from this vector to the hyperplane spanned by the rest of k minus 1 vectors. Okay, and then we know there's one way to compute this distance. For example, in 3 dimensions, we know the distance of vector c to the hyperplane spanned by vector a and b. So this h is just, you know, the volume of the parallel top dividing by the volume of the parallelogram, right? So this is what we know from elementary school. So we know the volume of this 3-dimensional body dividing by the area surface of this parallelogram will be the height. This is essentially the distance from C to A and B. Okay, so this is what we want to use. So then we know, you know, like the orthogonal part is basically the volume of the parallel top of this k wave function or k unit vectors. So I will omit them just to say f1 till fk, dividing by the volume of another parallel top spanned by the rest of k minus 1 vectors. Okay, so this is what we know from the previous slide. And then the next observation is that I know the volume of this parallel top is basically the determinant of these vectors. But of course, like these vectors have dimension like infinity, so I will look at the Gram matrix and compute the determinant and then take the square root. Well, the Gram matrix is of size k times k, so the entry JL is the inner product between the J's vector and the L's vector. So this is what we also know from college. So then, like all things are boiled down to bound the determinant of the gram matrix. Why? Because like we want to compute this orthogonal part, so we want to compute these two volumes. Then by this relation, we only need to control the determinant of these gram matrices. Okay. So our most technical lemma is to bound the determinant of the gram matrix. Okay. So this is saying like so this lemma is saying like for any frequencies f1 till fk, I look at the gram matrix of these k wave functions. So its determinant after taking square root is basically the pairwise product of all frequencies ij. It's essentially like the time window 2t times fi minus fj, but I will compare it with 1. And then there is like a distortion like k to the big O k square. Okay. So let me explain a little bit more why. So what's the relation between this and Hilbert's inequality? Okay. So recall that the Hilbert's inequality is saying like when all the frequencies have gap greater than 1/2t, so that's saying like this product is greater than 1. So they are basically orthogonal. So you can have this relationship. So this is saying like so this is saying like when the eta when fi if fi minus fj is greater than 1/2t, so this is saying like e to the 2 pi I f1t till e to the 2 pi I fkt are like almost orthogonal, such that we can have this relation that the expected L2 norm is the summation of the Fourier coefficients. Okay, and so then, yes. Right, that's like our drawback. No, we think it's not necessary, at least for special cases. But for the general case, this term we may need to change this term. Yeah. Okay, so let's compare this with Hilbert's inequality. So like Hilbert's inequality is saying like okay, under this condition, all these vectors are almost orthogonal. So this is the case. So if they are almost orthogonal, so you will realize like this determinant. So then if you check this this determinant will be some constant. Okay. So this determinant will be some constant. But if you look at our terminology, so when fi fj greater than 1/2t, so this term is at least 1. So then I will take the minimum between 1 and him. So this is 1. So the product of 1 is 1. So this is kind of like another way to understand Hilbert's inequality. Of course, like as Jerry pointed out, we have this distortion k to the OK square, and just like one technical issue in our proof, we don't know how to overcome. Yeah, so I want to say, this distortion is actually means we have both upper bounds and the lower bounds. So it's saying this determinant is at most k to the some constant times k square, but also at least some k to the minus k square. We have both. So that's why we can plug here, because like for the for the enumerator we need the lower bound, for the top part we need the upper bound. So we need both sides. I don't have time to discuss how we get this lemma, but you may already realize like this pairwise product comes from like a fundamental matrix. So we will just apply like a Cauchy-Burnett formula to expand this this inner product to expand this inner product into like a generalized like fundamental matrices, and then use Schur polynomial to compute each determinant. Okay, so I still have like 20 minutes. So as I said, like while this analysis is not tight, but we don't know how to improve at this moment. So back to the back to the key lemma. So we want to prove the key lemma. So this lemma will help us control the orthogonal part of each vector. So then we kind of like understand the relation. We kind of like understand the relation between the L2 norm and the coefficients. Of course, like to do this formally, we will apply like a net argument on the frequencies. But due to the time limit, I will not go over this part. Okay, so this is the key. So this is the first ingredient. So when the frequencies are clustered together, we can use polynomial to cluster together around 0. We can use polynomial to interpolate them. And then, so this is the recovery plan for general cases. So this general case is like we may have a cluster of frequencies not around 0, maybe very far away, maybe very far away. So then I will recover like a flag f tilde for this cluster. So this flag should be not far away from these frequencies. So then after recovering this flag, I will use the wave function of this flag e to the 2 pi I f tilde t times the polynomial to approximate its behavior. So the behavior of this cluster in the time domain. The reason is like after you times this wave function, essentially you shift this cluster by a minus f tilde factor. So you essentially shift this around 0. Yeah. So then the degree of the polynomial depends on how accurate is your flag and this k cubic factor. Okay. And if we have multiple clusters, we will recover multiple flag for each cluster. Okay. Okay. So now I want to tell you how we recover this flag. So this will be based on filter functions. And one thing under this filter function is the uncertainty principle. So let me go over this slide a little bit slowly. So we will design a pair of filter functions, essentially one function, but we want to control its behavior on the time domain and on the frequency domain. So we want that it will be close to the box function on the time domain. So box function is just like this function that's 0 outside of the time window, but that's 0 outside of the time window, but 1 in the time window. So this is a box function. So why we want a box function? The reason is that I can only observe my singular xt in the time window. So this is equivalent to I only have this singular xt times the box function, because the box function will erase everything outside of the time window, but keep everything in the time window. So given the limited observation in the time window, this is the same as I have this function xt times the box function. And then what I also want is Fourier transform to be compact, such that if I look at the Fourier transform of this function times box function, so this is equivalent to the convolution x hat convolvable with h hat. So I want this to be compact. So I don't want like h hat to be like has like a very long tail that destroy the structure of x hat. But unfortunately, this is impossible. Like I cannot have a function and its Fourier transform both compact by the uncertainty principle. So our solution will be we will keep its Fourier transform to be compact, such that this function will no longer be compact in the time domain. So it will have like a small tail go outside, but that will be fine. Like we will give bounds. We will control the growth of x outside of the time window. So we will control the growth of x such that the small tail of my field of h will erase or will kill the growth of x outside of the time window. So this is h times x in the time window. So it basically preserve what happens here, but it has like a very small tail that we can consider as noise. And then if we look at its convolution on the frequency domain, so this will be h hat. So it's a compact function. So I will take the convolution of this h hat with these 5 frequencies, then I get something like this. So while this looks a little bit like not in a very nice form, but they are very compact, because h hat is compact. So after convolution, this is also these 2 parts are also compact. So I can figure out, I can give a rough estimation. So this helps me. So this will help my algorithm to give a rough estimation of the original frequency, like the flag f tilde I mentioned before. Okay. So any questions so far? Yeah. So this is another algorithm ingredient. So we will use filter functions to recover these 2 flags. Okay. And then I didn't tell you. So then there are more things about Fourier sparse signals. I didn't have time to go over. So one thing is when we do the query on the input data, we should not use the uniform distribution. We should use a biased distribution towards the edge. So this is kind of similar to the Chebyshev distributions for polynomials. If you want to interpolate the polynomial, the right way to sample the points is from the Chebyshev distribution, not from the uniform distribution. And another thing is we want to control the growth of x outside of the time window. So this is the growth bound. So it basically control for t not in the time window. So how large could be x? How large could be xt compared to the expected L2 norm in the time window? Yeah. So that's the way we control the growth. So I think that's all the technical parts that I want to discuss. Let me know if you have any question. So finally, let me summarize and give some open questions. Okay. So basically, we give the first robust algorithm without the frequency gap condition. So the running time is we think it is sublinear. Its running time is polynomial in k and times and log ft. So it's quite robust. It guarantees that my approximation is close to x under any noise. We can also, subsequent works have extended this to signals with simple Fourier spectrum. And one technical ingredient that may be useful is we can give a rough estimation of the frequencies in x tilde. Okay. Sorry, in x hat. Okay. So some open question. So one question. So right now the sample complexity is k to the 4. So the main loss comes from the distortion factor in the determinant estimation that Jerry raised 10 minutes ago. So we have this k to the order k square distortion fact. So in fact, this will imply a frequency net of gap, basically k to the minus big O k square. We believe the correct gap of the frequency net. So to give a good to bound the sample capacity, we can just build a net for all the signals. But in here, signals could have arbitrary frequencies. So we will first give a net for the frequency. This is called the frequency net. We believe the correct gap in the frequency net should be 1 over poly k. In fact, k square may be enough. But we don't know how to prove this yet. And if we can show this will directly reduce the sample complexity to O tilde k square. Then we may be able to apply chaining to reduce it to linear, O tilde k. Another problem is to improve the time complexity. So right now, one loss in the time complexity is the polynomial degree is k cubic. But we know we know that if we stick on polynomials, say we just use polynomial to do interpolation, we just use polynomial times the basic wave function to do the interpolation. We know omega k square is kind of necessary. So this is saying polynomial interpolation may not be the best way to do, may not be the correct way to do the recovery. So you know, so it's open like any order family to interpolate K Fourier sparse signals. Also, you know, like another question is like, you know, if we can prove this, like, if we can get the correct net size, can we apply like dictionary learning on the frequency net? So that's another question. Yeah. So except like a sparse Fourier transform. So actually, like one question I feel like quite interesting from the practical side is like we know like FFT. When we design FFT, we always assume like n is the power of 2. You know, like when n is not a power of 2, say when n is 33, we say like, yeah, we say, oh, it's fine, we just pick the next 2 power, like 64 and run the FFT. But you know, like in practice, they really care about this loss of 2 because you kind of like blow the dimension by basically 2 factor. So can we save this 2 factor, you know, like in the discrete, in this for like the classic FFT? I think that's well, it may not be the best theoretical question, but I think it's still like a good like practical question. So yeah, that's all I had today. Thank you very much.
Wait, I thought one factor of t came from the filter functions as well. Did it not?
What?
I thought one factor of k from the sample complexity also came from the fact that you like do the
right.
filters.
Yes, you're absolutely correct. Like the it's like a yeah, it's like when we like you know estimate this cluster have like this flag f tilde, so the gap is something like a k square over t. There's like yeah, we cannot recover anything better than k square over t. You're right.
But then like the chaining will help you k, right?
Oh, but like you know, like for the sample complexity, we do not really care about the running time, right? We just care about like you know whether you can bound the L2 normal for all K Fourier sparse signals. I mean, that K square is this essentially that K square is this bottleneck, is this omega K square, but like it has nothing to do with the sample complexity, right? Thank you for the question. Yes.
So, any questions? If there's no any questions, let's thanks for Professor Chen again. This is a wonderful presentation.
Thank you.
And next, let's have a take break and come back at 2:15 p.m.